Hello, this video will help you with some background information on Lab 1, and this one focuses on scale. So we're trying to answer the question, how do maps represent the size of things compared with their size in real life? So your learning goals, what you're expected to be able to do after instruction practice, include interpret a map's scale, estimate horizontal distance and travel times using a map scale. Let's start with some definitions. A map scale communicates the size of a feature on a map compared to its size in real life. One of the main points of a map is to have a smaller version representing reality. So maps depict features smaller than they are in real life. A good map that is to scale will have the same proportions, the features in the same proportions as they are in real life. So the scale communicates those proportions. So here's an example. We've got a building, hypothetical building, that is 100 feet long in real life. And let's say we have a really big map. And on our really big map, the building length is only 10 feet. So it's a really big map. Not very realistic, but hopefully it's going to get us through some of our example ideas here. So two different kinds of scale. A verbal scale is something that describes the scale in words or numbers and uses a proportion. So in our example, the 10-foot length on the map to 100 feet in real life, the size of that house, we could represent as 10 feet to 100 feet. And we could simplify this by getting rid of a zero that's in both sides and also the units. So we could make this as simple as possible, this scale on our really big map, and say that the building scale on the map is 1 to 10, which means it's 1/10 the size that it actually is in real life. So yeah, that 10 feet length of a building on our map is probably not the most realistic thing ever. So let's use a scale that's a little more realistic. Let's try the building length on the map is 1 inch. So our verbal scale then would be 1 inch equals 100 feet. That is, anything that's 1 inch size on our map would equal 100 feet in real life. So our examples that we just used shows basically the two examples of how verbal scales are used. They're a proportion that it's expressed in words or numbers, showing the size of something on the map to its size in real life. And there's two different sort of proportional symbols that can be used. It could use a colon or an equals, and it turns out it depends on whether we're using units or not in our proportion. So if there are units, you'll usually have an equal sign. So our example from the last map would be 1 inch equals 100 feet. That's sort of, in a sense, self-explanatory. That's as simple as it gets, and you might see this, or 1 inch equals a mile. So different units, we use the equal sign in between. Another version of verbal scales can be unitless. That is, it's without units. And usually scientists and people doing the math like this better because if you've done unit conversions, which we're going to do a little bit of, they can kind of be in a pain in the butt. But in order to get the scale to be unitless from the information we have, we actually have to do a little bit of math. So usually the unitless verbal scales will have a colon showing what the proportions are. So if we want to make this is our assignment, so we better do it. We want to figure out what the unitless verbal scale would be, and we know that our scale is 1 inch equals 100 feet. What do we do to get it to be 1, and we can put the colon to something else? We need to get everything in the same units. So how do we do this? This is sort of a review or maybe a lesson in unit conversion or unit analysis, as it's called sometimes. And it doesn't need to be complicated, so I'm going to give you kind of the general pattern, and then you're going to give it a whirl on the next example. All right, so we start with what we know. We start with what we want to convert, and we're going to put it in a fraction form. So here, because we want everything inches, we're going to take that 100 feet because we want that to be put into inches. we're going to divide this by 1 basically, which doesn't really mean anything. That is, it doesn't really change the number, but that's okay because having it in fractional form's going to make us a little bit easier to write this out. So let's start with what we want to convert, 100 feet over 1. We're going to multiply by a conversion factor. Our conversion factor is something we can look up or something we can basically make up using what we know. So we're going to write one out, and in this case our conversion factor we're going to use relates the units we have, which are feet. We're going to put that on the bottom of our fraction in the conversion factor to the units we want, which is going to be inches, and it must be equal to 1. So hopefully somewhere in the depths of your memory you have the idea that 12 inches equals 1 foot. They are equivalent to each other. So we can put our fraction 12 inches over 1 foot. This is great because it means we can get rid of those feet units, and we are then going to multiply through. So what we get is 100 feet, well, really 100 because we've canceled the units, multiplied by 12. That gives us 1,200 inches. So what that means is our 100 feet is actually 1,200 inches. Those are equivalent, but now we've got everything in inches, and so we can have our verbal scale expressed 1 to 1,220. Okay, so now it's your turn to practice. So let's say we go to that example I gave earlier. You discovered that 1 inch on a map is equal to 1 mile in real life. One way to express this scale is 1 inch equals 1 mile, but what if you want to or you needed to convert it so you knew how many inches are in a mile? So that's kind of what we need to know. It would be really helpful to just know how many inches are in a mile, or you can do it in steps with inches in a foot and feet in a mile. So it's sort of your choice. I'm going to walk through the version that has inches in a foot and feet in a mile for you after you get a chance to work this out. And usually what we want to do is convert it all to the smallest unit as we did before. So we want to figure out how many inches are in a mile so that we can figure out the verbal scale with the 1 and then the colon, then however many inches that thing that's 1 mile in real life would be. All right, so please, you can go back to the sort of list of steps earlier in the video. Take a couple minutes, see what you can work out, what the scale should be, and then unpause the video again, and I'll walk you through the way I did it. So please really try to do this on your own first. It's going to make a huge difference. Even if you don't get it right, it actually is very research-based, valid strategy to give it a try first. All right, so give it a try. Okay, so let's try this. We're going to start with what we want to convert as a fraction over 1. So we want to convert 1 mile. So let's put 1 mile over 1. We're going to multiply by a conversion factor relating what we have, which is miles, to what we want. In this case, we're going to go first from feet in a mile and then inches in a foot. So you may or may not remember how many feet are in a mile. This happens to be one of these things I've used enough times that I now have it in my brain, but it's also okay to look that up. So it turns out there's 5,280 feet in a mile. So how are we going to set this up? We want the miles to cross cancel, so the 1 mile is equivalent to 5,280 feet. The 1 mile is going to be on the bottom of our conversion factor, and the 5,280 feet is going to be on top. All right, and then we actually are going to use a second conversion factor here. And again, if you looked at how many inches are in a mile, you probably just have one conversion factor, and that's fine too. We should get the same answer, so let's see if we do. Our second conversion factor relates feet to inches, and we want to get rid of that foot as a unit. So we're going to put 12 inches on the top of our fraction and 1 foot on the bottom. And then hopefully you notice we get rid of all the units this way. And if we multiply through 1 mile times 5,280 feet times 12 inches, hopefully you got 63,360 inches in 1 mile. And now we can write the verbal scale as 1 to 63,360. See if you got the same answer. The other kinds of scale that we see commonly on maps used in geology, besides the verbal scale, is a bar scale. And bar scales always have units. What they will do is show a line or a box of a certain length that would be equivalent to the units that are given in numbers in real life. So let's give our example again of that house that is 100 feet long. If we had this on the map, there would be a bar or a line that's exactly the length of that building, and it would be labeled 100 feet. So it might have a different length. Maybe it would be 1/10 of that, and it would say 10 feet. But in any case, it's going to show what the length proportionality should be by using a line or a box. So more typical scale kind of thing on a map would look like the one to the right, where it's got more than just one bar. It's actually got two different sets of units. It's got kilometers, and I don't even know what that other thing is. Doesn't even make any sense, but we're not going to worry about it. I think it's related to latitude and longitude. Weird, huh? Okay, so, and then notice there's sort of a 0 point, and then usually it goes the opposite way from 0 and gives some smaller units. So these should be 20, actually they're not, they're 25, 50, 75, and 100 there. I figured it out. It's nautical miles, so it's something that's useful for if you're in the water or if you're on land. So it's slightly different than a regular mile, and I don't remember why that is, but it's nautical miles. So our last task to be able to figure out is a bar scale to measure the straight line distance between 2 points. And I think I lied. I think this is our second to last thing, but let's walk through a strategy for doing this. You can use a ruler. There's a ruler in the back of your course pack, most likely your lab pack, but a piece of scrap paper works just as well. What you want to find is this piece of scrap paper that's longer than the line you're measuring. The advantage to using scrap paper is you don't need to try to convert the scale to exactly whatever inches or centimeters or millimeters or whatever's on your ruler. You can just use the scrap paper and the scale that's on the map. So take your scrap piece of paper. You can even do this on the computer. Hold that scrap piece of paper up and make a mark, a tick mark or a short line at each end of the line you're measuring. So in this case, we're measuring the distance between those points A and B, both in Florida, basically along the northern part of Florida, as far away as you can get from each other. And notice my little scrap piece of paper indicated there. I've now marked pretty precisely the middle of those 2 points where there's located. Okay, so let's see in the next bit what we're going to do. The next step would be to move your scrap piece of paper down to the bar scale, in this case the kilometer scale, and line up one end with the 0 mark. So next, make a mark on the paper at the farthest measured line on the scale and note its length. In this case, I've made a mark to 400 kilometers. And then we're going to use the scale again to estimate the total length. And in fact, we're going to do better than that. We're going to use the smaller scale off to the left with those intermediate lines. And we're going to try to measure as precisely as possible. So it looks like I've gone another 100 kilometers between points A and B, and then the smaller marks that are 25 kilometers each, looks like I've gone 3 of those approximately, maybe just a little bit more, but I'm gonna estimate and say it's about 575 kilometers total. So now let's use what we know about that distance, that 575 kilometers, to estimate the amount of time it would take to travel that distance. So we kind of do this a lot in Michigan. We talk about, oh, how far is that away? Oh, it's about an hour, right? So this is a way maybe that we ground that kind of discussion in actual numbers. Okay, so we know the distance A and B is 575 kilometers. Let's say a small airplane can travel 300 kilometers in 1 hour. So we've got that 2 pieces of information. And now we've got our question. But there's sort of another piece of information in there too. So it says, assuming that refueling at location B took less than an hour, can you travel from A to B and then back again in 3 hours? So sort of imagining we all have small planes and there's no COVID and whatever else. You gotta bear with me just a little bit here, right? I know. So then it's asking you to explain your reasoning. Okay, so take a couple minutes and see what you think. What's the best answer? If it can go, we can go 300 kilometers in 1 hour. Think about the total distance it would be to travel from A to B and then back from B to A. And can we do that in 3 hours total? So, according to my reasoning at least, the best answer would be no. We cannot travel from A to B and then back again if refueling, even if refueling took less than an hour. Can we do that in 3 hours? We can't. So the trip each way is 575 kilometers, which is almost double what we can do in an hour. So if we can fly 300 kilometers in 1 hour, that means we'd probably do about 600 kilometers in 2 hours. So that means each way, A to B and B to A, is going to take just a little bit less than 2 hours. So that means the whole round trip would take likely more than 4 hours unless you could refuel in 5 seconds. But you definitely couldn't do it all in 3 hours. Okay, I hope this helps you get a sense of how to use scale, how to practically measure it, and how to think about the time travel kind of thing here. Not literally time travel like going back in time, but how do we use travel time would be a better way to say it, to figure this out.